Good afternoon, class. For today's class in the elementary statistics and probability, we're now in week 5 of our discussion. And we, the group 5, will discuss the topic for today, which is probability. But before we formally start our discussion, I just want to remind you about the mission and vision of our school. So now let us know the objectives of this topic. After completing this topic, students should be able to understand the concept of sure and impossible events. Also to determine the properties of a valid probability measure. To determine the probability of mutually exclusive event, complement of an event, conditional event or conditional probability, and also the independent events. So like what I've already said, we're now in week 5 of our discussion, which is probability. First, let us know what is the definition of probability in statistics. Probability is calculated on the basis of available data or frequencies or pre-experiences. We all know that probability means possibility. Probability is a measure of the likelihood of an event to occur. The formula of probability is P equals R over N, which means probability is equals to relative frequency over the number of items. So, here's the things that helps us fully understand what is probability. Let's start with the question of what is the probability of pig fly? Can a pig fly? No, it cannot. The probability of a pig able to fly is 0. Okay? Another one, what is the probability of getting a natural number on a roll of a pair die? No matter how the die is rolled, you will get a number between 1 and 6. All of that are natural numbers. The probability is 1. We will definitely get a natural number on the roll of a pair die. A probability of 0 also means there is a 0% chance of the event occurring. It is an impossible event. On the other hand, a probability of 1 tells us there is a 100% of chance of the event occurring. It is a certain or sure event. Okay, that brings us to an important point of this topic. The probability of every event will lie between 0 and 1 inclusive. Now, here is the definition of sure event and impossible event. When we say sure event, it is an event which is sure to occur at every performance of an experiment. Sure event is also called certain event. It is also the one that contains the whole sample space. And I will going to show following examples later. And now, when we say impossible event, it is an event which cannot occur at any performance of an experiment, which is opposite to the sure event. Because impossible event is when the event does not contain any element of the sample space. Also, I'm going to show some following examples regarding this one. An event A is called a sure event if the probability of event is equals to 1 or P open quantity E is equals to 1. This happens when all outcomes of the experiment are favorable event. For example, in throwing a die, the event of getting a natural number less than 7 is a sure event. A sure event is an event which is always happen. It is sure event because getting a natural numbers in throwing a die, which is 1 through 6, are less than 7. So that, again, this is an example of a sure event. Head or tail is one of the certain or sure event because it is connected in tossing a coin. The head and tail are the sure outcome in tossing a certain coin. Faces of a dice. So we all know that we have 6 faces in a certain die. So the phase 1, phase 2, phase 3, phase 4, phase 5, and phase 6 is a sure event connected in throwing a die. Here's another example. A teacher chooses a student at random from a class of 30 girls. The question is, what is the probability that the student is a girl? So, probability of girl is equals to 30 over 30 or equals to 1. Because since all of the students in the class are girls, the teacher is certain or sure to choose a girl. A glass of jar contains 15 red marbles. If a single marble is chosen at random from the jar, what is the probability that is red? So, probability of red is equals to 15 over 15 or equals to 1. Choosing a red marble is sure to occur since all 15 marbles in the jar is red. So this is an example of a sure event. Let's now proceed to impossible event, which is an event A is called impossible event if the probability of event is equals to 0. This happens when no outcome of the experiment is a favorable outcome. For example, in throwing a die, the event of getting a natural number greater than 6 is an impossible event. Because, as we all know that the certain die consists of 6 faces, which is numbers 1 to 6. That is impossible to have an outcome greater than 6. Here's another example of impossible event. A spinner has 4 equal sectors colored green, blue, red, and yellow. The question is, what is the probability of landing on purple after spinning the spinner? So, probability of purple is equals to 0 over 4, which is equal to 0. Because it is impossible to land on purple because the spinner does not contain this color. For example, we all know that one standard deck of cards consists of 52 playing cards, which has 4 suits, which is heart, clubs, spades, and diamonds. Each suit has 13 cards, which is ace, dust, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. And also we have face cards, which is jack, queen, and king. There are no joker cards. There are only 4 of a kind. For example, 4 of tens or 4 tens. So the situation is this. A single card is chosen at random from a standard deck of 52 playing cards. The question is, what is the probability that the chosen is a joker card? So the probability of joker is equals to 0 over 52 or equals to 0 because it is impossible to choose joker card since a standard deck of cards does not contain any joker. So this is also an example of an impossible event. So here's the last example of impossible event. A total of 5 cards are chosen at random from a standard deck of cards of 52 playing cards. What is the probability of choosing 5 aces? Probability of 5 aces is equals to 0 over 52 or equals to 0. Is that because it is impossible to choose 5 aces since a standard deck of cards has only 4 of a kind. So, this is also an example of impossible event.
Referred to as the axiomatic definition of probability, where the 3 properties give the 3 axioms of probability. These 3 axioms are all we need to assume about the operation of probability to hold, which we now state. For this slide, we use the property of probability for event that we can derive by simply assuming the 3 axioms are true. Properties of probability measures. Let S be a sample space with probability measure P. Also, let A and B be any event in S. Then the following hold. So the first property state that 1 minus the probability of an event gives the probability of this complement. The second probability is the probability of empty set is 0. Third, if the event A is subset of event B, then the probability A must be less than or equal to the probability B. Then the fourth, the probability of any event is less than or equal to 1. And finally, the addition law, which states the probability of the union or of any event A and B is given by the probability of event A plus the probability of event B minus the probability of their intersection. Can you prove the 5 properties of probability measure stated above using only the 3 axioms of probability measure? For the first property, note that by definition of complement of an event A, we have A is disjoint union of event A of its complement is equal to S. and A, intersection of event A of its complement is equal to empty set. In other words, given any event A, we can represent the sample space S as a disjoint union of A with its complement. Thus, by the first and the third axiom, we derive the first property. 1 is equal to the probability of sample space is equal to the probability of event A, disjoint union of event A with its complement, is equal to the probability of event A plus the probability of event A with its complement. Probability of event A with its complement is equal to 1 minus probability of event A. The second property. For the second property, note that we can write sample space S is equal to S union of empty set, and that this a disjoint union. Since anything intersected with the empty set will necessarily be empty. So using the first and third axiom, we derive the second property. 1 is equal to probability of sample space is equal to the probability of sample space disjoint union of empty set is equal to probability of sample space plus probability of empty set is equal to 1 plus probability of empty set. Then, the probability of empty set is equal to 0. The third property. For the third property, note that we can write probability of event B is equal to the event A, disjoint union of probability of event B, intersection of event A with its complement, and that this a disjoint union. Since event A and event A with its complement are disjoint. By the third axiom, we have probability of event B is equal to the probability event A, disjoint union of the probability of event B is intersection of event A with its complement, is equal to probability of event A plus the probability of event B intersection of event A with its complement. By the second axiom, we know that probability of event B intersection of event A with its complement is greater than or equal to 0. Thus, if we remove it from the right-hand side of this equation, we are left with something smaller, which proves the third property. The probability of event B is equal to the probability of event A plus the probability of event B intersection of A with its complement is greater than or equal to the probability of event A. Then, it implies the probability of event B is greater than or equal to the probability of event A. The fourth property. For the fourth property, we will use the third property that we just proved. By definition of any event A is a subset of the sample space S, that is, A is an subset of sample space S. Thus, by the third axiom, we derive the fourth property. Probability of event A is less than or equal to the probability of sample space S is equal to 1. It implies the probability of event A is less than or equal to 1. The fifth property. For the fifth property, note that we can write the union of event A and B as the union of the following disjoint event. In other words, the union of A and B is given by the union of all the outcomes in A, with all the outcomes in B, but not in B. Furthermore, note that event B can be written as the union of the following two disjoint events. In other words, B is written as the disjoint union of all the outcomes in B that are also in A, with the outcomes in B that are not in A. We can use this expression for B to find the expression for probability of event A with its complement intersection of event B. To substitute in the expression for event A union of event B in order to derive the fifth property. The probability of event B is equal to probability A intersection of B implies the probability event A with its complement is intersection of event B. Then it implies the probability of event A with its complement is intersection of event B. Then it is equal to probability of event B minus the probability of event A union to event B. Then the probability of event A union to event B is equal to the probability of event A plus the probability of event A with its complement is intersection of event B. Then it implies the probability of event A union to event B is equal to the probability of event A plus the probability of event B minus the probability of event A is intersection of event B. However, there's another abstract approach for defining what probability is, and there's more empirical approach to defining probability that uses what is the uses of relative frequency approximation. As stated here, the approximation uses the relative frequency of the number of times of event A occurs out of the total number of repeated trials on the underlying probability experiment, and that ratio is what to use is to estimate the probability of A. For example, consider our experiment is tossing a coin twice. If we would know the probability of getting one head, which our event A in the previous example, then we repeatedly toss a coin twice and count how many times and how many outcomes has at least one head. Let's say we repeat the two tosses in 100 times and get at least one head in 73 times, and the ratio is 73 divided by 100 provide the estimate probability in getting at least one head in two tosses of coin. Now, we can see why probability frequently interpreted as percent, because 73% of those 100 tosses resulted in the outcome in our event. Interest for the example. In other words, this relative frequency approximation are percentages of the current of the event repeated trials of the event of the probability experiment.
Hi, I'm Sir DJ, and now let's discuss about priori approach. A priori approach is a probability that reduces from formal reasoning. In other words, a priori probability is derived from logically examine an event. A priori probability does not vary from person to a person as would a subjective probability, and it is an objective probability. The formula of priori probabilities equals to F over N, where F refers to the number of desirable outcomes and N refers to the number of total of outcomes. Note, this formula can be only used for events where outcomes all have equal odds and occurring and mutually exclusive. For example, a six-sided fair dice is rolled. What is the priori probability of rolling a 2, 4, or 6 in a dice roll? The number of desired outcomes is 3. Rolling a 2, 4, or 6, and there are 6 outcomes in total. The priori probability, for example, is calculated as a priori probability is the equals to 3 over 6, which is equals to 50%. And the second example, deck of cards. In the standard deck of cards, what is a priori probability of drawing an ace of spades? The number of desired outcomes is 1, which is an ace of spades. And there are 52 outcomes in total. The priori probability is equals to 1 over 52 is equals to 1.92%. Therefore, the priori probability of drawing an ace of spades is 1.92%. Now let's move here in a posterior approach. The posterior probability is calculated by updating the prior probability using Bayes' theorem. A posterior probability Bayesian statistic, it is a revised or updated probability of an event occurring after taking into consideration new information. Also, the posterior probability is those resulting distribution P, the quantity of A and B. In statistical term, the posterior probability is the probability of an event occurring given that event B has occurred. This is Bayes' theorem formula, where AB is equal to events P, the quantity of B, and A is equal to the probability of B occurring given that A is true. P, the quantity of B, and P, the quantity of B is equal to the probability of A occurring and B occurring independently of each other. For example, we're going to see an incredible powerful theorem is a probability which is Bayes' theorem or Bayes' theorem. So here the example, if you have a couple and they got 2 different children and you're asserted that is at least one of those children is going to be a girl. But what is the probability that both that children are going to a girl? So let's push this formula. So I'm asking in effect, I want to know what is the probability of 2 girls given that we're gonna have at least 1 girl. Well, then this is my theorem tells me that this is a probability I'm gonna be abbreviate even more, just go all the way down to 1 girl. I mean at least 1 girl, but I will write 1G. Given that I have 2 girls multiplied by P of A here. P of A is the first thing, so multiplied by the probability of 2 girls. And then finally divided out by probability of B. So this is a probability at least 1 girl, which I abbreviate to the probability of 1G. Alright, so we have a computation, so we can actually go and evaluate it now. Well, let's look this conditionally probability, the probability of having 1 girl, given that you know there are 2 girls. So the P of 1G given the 2G is really easy to compute, which is equals to 1. Next is what is the probability of there being 2 girls. Well, you might remember that the 4 cases are girl, 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 boy, boy, girl, and boy, boy. There were 4 different sort of probabilities. We're gonna be investigate, so this is we can get 1/4, which is the probability of having 2 girls, and then we're going to divide it by at least one girl. Also, we get 3/4 from the possible that there is a girl. And our final answer is 1/3.
Subjective approach. It says that a probability based on a guess or estimate from some knowledge or relevant circumstances. It is use your opinion to find probability. Subjective approach is a type of probability derived from an individual personal judgment or own experiences about whether a specific outcome is likely to occur. It contains no formal calculation and only reflects the subject's opinion and past experiences rather than a data or computation. It is differ from person to person and contain a high degree of personal biases. It is also says that it is an estimate of a likelihood of an event based on intuition and experiences, making an educated guess using statistical data. Probabilities only have meaning to the person's thinking about and being subjective when calculating probabilities in a way of quantifying the unknown and is a necessary part of life. For example, a flip coin will show tails. Its probability is maybe because it has a 50-50 chance that show tails. I will be in school tomorrow. It is likely or probable. I will roll a tree using a die. It is maybe because it has a 50-50 chance also that it show tree when he roll a die. I will have vegetable with dinner tonight. It is likely or probable. I will not get dark tonight. It is impossible. Law of large number. In probability and statistics, it states that as sample size grows, it means get closer to the average of whole population. The law of large number in financial context has a different connotation, which is that a large entity which is growing rapidly cannot maintain that growth pace forever. It states that even random events with a large number of trials may return stable long-term result. However, each additional trials increases the precision of the average result. The law of large number is a theorem that describes the result of repeating the same experiment a large number of times. The large number states that the same experiment for a study is repeated independently a large number of times. The average of the result of the trials must be close to the expected value as the number of trials is increased. Central limit theorem. Average losses from a random sample of n exposure units will follow a normal distribution. Regardless of the population distribution, the distribution of sample mean will approach the normal distribution as the sample size increases. The standard error of the sample mean distribution declines as the sample size increases. For example, a single roll of six-sided die produces one of the numbers 1, 2, 3, 4, 5, or 6, and each with equal probability. 1 plus 2, 3, plus 3, 6, plus 4, 10, plus 5, 15, plus 6 is 21. 21 over 6 is equal to 3.5. Therefore, the expected value of a single die roll is 3.5. Another example, we rolled the dice 3 times and the outcomes were 6, 6, and 3. 6 plus 6 is equal to 12 plus 3 is equal to 15 divided by 3 is equal to 5. Therefore, the expected value of a dice events is 5. According to the law of large number, if we roll the dice of large number of times, the average result will be closer to the expected value. Forms of large number. First, the weak law of large number. It states that the sample average converges in probability towards the expected value. In interpreting this result, The weak law essentially states that for any non-zero margin specified no matter how small, with sufficiently large sample, there will be a very high probability that the average of the observation will be close to the expected value. Convergence in probability is also called the weak convergence of random variables. This version is called the weak law because random variables may converge weakly in probability as above without converging strongly or almost surely as below. Example, we start with some probability distribution. It has a certain mean and variance which we assume to be finite. Then we draw independent random variables out of the distribution so that these xi are independent and identically distributive, or IID for short. We calculate the average of the value that has obtained and that give us so-called sample mean. Notice that the sample mean is random variable because it has function of random variable. It should be distinguished from the true mean. Calculate its expectation. It involves two kinds of averaging. The sample mean averages over the values observed during one long experiment, whereas the expectation averages over all possible outcomes of the experiment. The expected value of sample mean by linearity, it is the expected value of numerator divided by denominator using linearity once more than the expected value, and since each one of these expected value is equal to mu, we obtain n times mu divided by n, in which leave us with mu. Let us now calculate the variance of the sample mean. The variance of random variable divided by a number is the variance of that random variable divided by the square of the number. Therefore, we obtain n times the variance of each one of them with sigma square over n. The Chebyshev inequality means the distance of random variable from its mean being larger than certain number has probability that bounded above the variance of random variable of interest divided by the square that numbers. Quantity sigma squared over n times epsilon squared, and let n go to infinity, then use obtain eliminating value of 0. If we fix any particular epsilon, which is supposed inconstant, the probability that sample mean force away the true mean by more than epsilon, that probability becomes smaller and converges to 0 and goes to infinity. The second form of law of large number is the strong law of large number. It states that the sample average converges almost surely to the expected value. The proof is more complex than that of the weak law. This law justifies the initiative interpretation of the expected value of random variable when sampled repeatedly as the long-term average. Example: if we take omega and sample space, remember that the random variable are function from sample space to real number. x1 omega, x2 omega, x3 omega, and so on is a sequence of 4s and 10s. With probability 1, the running average of the sequence will converge to 7. Suppose the first 10th term of the sequence has the values 10, 10, 4, 10, 10, 4, 10, 4, 10, 4. Then, the first term in the running average are, the first number is 10 divided by 1 is equal to 10. The second number is 10 plus 10 divided by 2 is equal to 10. The third number is 10 plus 10 plus 4 divided by 3 is equal to 8. The fourth number is 10 plus 10 plus 4 plus 10 is divided by 4 is equal to 8.5. The fifth number is 10 plus 10 plus 4 plus 10 plus 10 divided by 5 is equal to 8.8. The sixth number is 10 plus 10 plus 4 plus 10 plus 10 plus 4 divided by 6 is equal to 8. The seventh number is 10 plus 10 plus 4 plus 10 plus 10 plus 4 plus 10 divided by 7 is equal to 8.28. The 8th number is 10 plus 10 plus 4 plus 10 plus 10 plus 4 plus 10 plus 4 divided by 8 is equal to 7.75. The 9th number is 10 plus 10 plus 4 plus 10 plus 10 plus 4 plus 10 plus 4 plus 10 divided by 9 is equal to 8. And the 10th number is 10 plus 10 plus 4 plus 10 plus 10 plus 4 plus 10 plus 4 plus 10 plus 4 divided by 10 is equal to 7.6. As the sequence continues, the running average will converge to the mean 7 and probability 1.
Next, mutually exclusive event. The mutually exclusive event are the things that can't happen at the same time, which is there is no common between two or more events. If A sub 1 and A sub 2 are two mutually exclusive events, then A sub 1 intersection A sub 2 is equals to an empty set. Here's the first example. Two events don't have any common point, which is if S is equals to 1, 2, 3, 4, 5, and 6. E sub 1 and E sub 2 are two events such that E sub 1 consists of numbers less than 3 and E sub 2 consists of numbers greater than 4. So, E sub 1 is equals to 1 and 2 and E sub 2 is equals to 5 and 6. Then, E sub 1 or the event 1 and event 2 are mutually exclusive. Another example, in connection with throw a die, even phase and odd phase are mutually exclusive. As you can see in the illustration presented, the even phase are 2, 4, and 6, and odd phase are 1, 3, and 5. So, this is an example of mutually exclusive event. So, let us consider on throw a pair of dice. So, these are the possible outcomes. We can get one number between 1 to 6. Let us consider two events, A and B, and understand if they are mutually exclusive or not. In event A is getting an even numbers, and in event B getting an odd numbers. Remember, we have to consider just one throw. Assume we get at the first throw, which is 2, so that is an even number, not an odd. And if we get in our second throw is 5, so that is an odd, not an even. So this means that if we get an odd number, that is not an even. So vice versa. So these two events cannot occur together, and hence it is a mutually exclusive event. Now look at another case. Let's say that our event A is an odd numbers and event B will be getting a numbers less than 4. Are these events are mutually exclusive? Let's see. When we get 1, it is an odd number and also a number less than 4. Also the same if we get 3, it is also an odd number and a number less than 4. These two events can happen together, so it tells us that they are not mutually exclusive. So I just want to share that when we say independent event or independent, this is not related. And mutually exclusive are cannot occur together. In probability, the complement of an event is the outcomes in the sample space that are not part of an event. For example, if we were rolling a die and we assigned the event to be rolling 1 or 2, The complement of that event is rolling a 3 through 6. Our event is written as P of E, which is probability of event E, and the complement of an event is written as P of E prime with little apostrophe here. And there are few rules or equations that go with complementary events. Looking at the sample space of a die roll, we know that each of these has probability of 1 over 6. And when we add them up, we can get 1. So, all of the probability of all outcomes in the sample space is equals to 1 or 100%, which that knowledge, the probability of event E plus the probability of E prime is equals to 1. For instance, in our example, rolling a 1 or 2, that would be the probability of event E. And A rolling a 3 through 6 will be the probability of E prime or E complement. So if we add the probability of E and the probability of E prime, we will get 1. To see it visually, we can look at this Venn diagram. Here is a square and the area inside the square is equals to 1. If we put circle in the area and let the circle represent the probability of E, and the area outside the circle will be represent the probability of E prime. So if I said that the area of probability of E, which is the circle, is 0.35, then 1 minus 0.35 is equals to 0.65. And it is the area of probability of E prime. So, as you can saw, we can use this equation two other ways. First, we can subtract the probability of E prime from both sides. So, have probability of E, which is equals to 1, minus the probability of E prime. Or again, from our original equation, we can subtract the probability of E from both sides to get the probability of E prime is equals to 1 minus the probability of E. And this equation can come handy for instance. So let's say you poll 50 people and ask what is your favorite sport. Using the frequency table, 29 said football, 11 said basketball, 6 said baseball, 3 said soccer, and 1 said tennis. Based on the data in this table, what is the probability of a person's favorite sport not football? So, to answer this, we can use our equation of probability of E prime is equals to 1 minus the probability of E in the equation. So, this equation, the event E is a probability that football is a person's favorite sport, which is 29 over 50. And the probability of E prime is equals to the probability of football is not person's favorite sport. So, the probability of E prime is equals to 1 minus 29 over 50. So, doing the sum mathematics, we can get 50 over 50 minus 29 over 50, which is equals to 21 over 50. And also equals to 0.42 or 42% of selecting some whose favorite sport is not football. So, in calculating probabilities, these equations are very useful in many situations.
The conditional event or the conditional probability. Conditional probability is the probability of an event E2 occurring the given of the event E2 has already occurred. This how you know the situation of the probability of E sub 2 given the E sub 1 is equal to the probability of E sub 2 and E sub 1 divided by the probability of E sub 1. The one thing that we need to keep in our mind is it is great to have this formula to help ourselves. But if we can make a sense of the situation, then we have to rely on this formula. And we can actually understand what's happening. For the first problem, we're going to focus using the two methods. One is just the basic formula, and second method using the conditional probability formula. And here's the problem. You roll one 6-sided die. What is the probability of a 3 given you know the number is odd? So for the first method, the probability of a 3 given we know it is odd if we take about logically. If we know the numbers are odd, then we do is the total number of outcomes. There's 3 numbers from 1 to 6 are odd. 1, 3, and 5. So the 3 possible outcome given we know that is odd, then there's one odd number that is 3, then the probability is 1/3. Now, let's look back at the conditional probability formula. Let's apply this and we'll get a same answer. Then it will be equal to the probability of growing 3 and an odd divided by the growing odd when the probability of the growing 3 and odd is 1/6 divided by the probability of growing odd would be 3/6 is equal to 1/6 times 6/3. Then we can see the answer is the same. Then we have 1/3. Maybe we're asking why we uses the conditional probability formula, since we notice it's more complicated. But in the some cases, it will be appropriate as we see in the next problem. The next example is at P-Town High School. The probability that a student takes computer programming and Spanish is 0.15. The probability that a student takes computer programming is 0.4. What is the probability that a student takes Spanish given that the student is taking computer programming? The probability of a student taking Spanish and computer programming divided by the probability of students taking programming. Then, we can remember that E sub 1 is the attempted occur based upon these questions. The student taking computer programming. So, the probability of taking Spanish and computer program is 0.15 divided by the probability of taking a computer programming is 0.4. Then, it is equal to 0.375. It will be expressed 37.5%. And again, what is tell is the student taking computer programming. Then, there's a 37.5 chance that they were Spanish as well. Let's look to another example. Here are the results of a survey completed with adult parents with children. And they had a child in college and child not in college. They asked that college is either too expensive, affordable, or too cheap. And here is the question, what is the probability of a person thinks college is too expensive given they have a child in college? So, the only concern about if the person in the row of child in college. What is the probability that they think colleges is too expensive? So, looking our formula, here is equal to the probability that adult parent thinks colleges is too expensive and they have child in college, which is 55% Then, let's write in decimal form as 0.55 divided by the probability of event 1, which they have child in college, which is in the entire row of child in college. The probability that they have in college is 55% plus 4% is equal to 59% or 0.59. Let's look this logically. If we only consider the parent with the child in college, this 59% as we see in the denominator, and all 59%, this 55%, this is the portion that college is too expensive. So, let's go ahead dividing this one. 0.55 divided by 0.59 is equal to 0.932 or 93.2%. So, we can see that most of them tell that college is too expensive compared the small percent of affordable.
So now let's discuss the independent events. When two events, A and B, are independent, the probability of both occurring is the probability of A and B is equals to the probability of A times the probability of B. So event A and B are independent events if the probability of B occurring is the same whether or not event A occurs. Now let's take a look with this example. You flip a coin and pack one card out of the hat containing 20 cards numbered 1 to 20. So what is the probability of getting heads on the coin and getting a number greater than 15 from the hat? So we want to know is the probability of flipping a coin and getting a head and picking a number greater than 15 from the hat. So we will say n and it is greater than 15 because these two are independent event and this probability is equals to the probability of flipping a head times the probability of something a number is greater than 15 from the hat. So the probability of getting a hand on the flip coin would be 1/2 because there are two outcomes. One of these is favorable outcome times the probability of selecting a number greater than 15. So, there are total of 20 possible outcomes. To determine how many favorable outcomes there are, so notice how there are 5 numbers greater than 15, which is 16, 17, 18, 19, and 20. So this would be 5 over 20. So to calculate this one is 1/2 times common factor of 5 and 20, which is they are factorable, so we have 1/4, which is equals to 1/8. So we can get or we can say that the probability of flipping a head and selecting a number greater than 15 is equals to 1/8 or 0.125 or 12.5%. You roll a pair of dice twice. What is the probability of a 3 on the first roll and even number on the second roll? So we want to find the probability of rolling a 3 and uneven in the second roll. So because these two events are independent, this is equals to the probability of rolling a 3 times the probability of rolling an even number. So the probability of rolling a 3 is one favorable outcome out of 6. So that would be 1/6 times the probability of rolling an even number. So, we will have 2, 4, and 6 are even. So, there's a 3 favorable outcome out of 6. Simply 3 over 6 or 1 half. So, 1 over 6 times 1 half is equals to 1 over 12. Okay? So, we can say that the probability of rolling a 3 and on the second roll is an even number is equals to 1 over 12 as a fraction or equals to 0.083 repeating, or we can simply write this one as 8.3%. Let's take a look at this one left example. A card is pulled, a deck of cards, and noted. The card is then replaced. The deck is shuffled, and a second card removed and noted. So what is the probability of both of cards are face cards? So we all know there are total of 52 cards pictured here. So where 12 of them are face cards, which is jacks, queens, and kings, and one of each suits, and there are 4 suits. So what is the probability of face card and another face card at the second time? So there's a replacement. So these two events are independent. If there wasn't replacement, they would not independent. But because this is independent, this is equals to the probability of a face card times the probability of another face card. Again, there are 12 face cards out of the total 52 cards. So this would be 12 over 52. So let's share a common factor of 4. So both of these fractions simplify to 3 over 13. Okay? So we have now 3 over 13 times 3 over 13 is equals to 9 over 169. Let's go express this again in 3 ways, which is probability of face card and face card as fraction is equals to 9 over 169. So we can get a 0.0533, which is in percentage, we have 5.33%.
Operation of probability. If we have two events, A and B, of the same sample space E, A is included to B, ACB, if every outcome of A is an outcome of B, where operation of probability consists of 3 events: the union, intersection, and complement. In the illustration, it shows the union event. So, a union event, A union B, is the event that happens either A or B occurs. It is the collection of all outcomes that are elements of one or other of the set A and B or both of them. It is an act or instance of uniting or joining 2 or more things into one. Example: if set A is equal to 1, 3, 5, 7 and B is equal to 1, 2, 4, 6, 7, then the A union B is equal to 1, 2, 3, 4, 5, 6, 7. A more elaborate example involving 2 infinite set is A is equal to X is an even integer larger than 1. B is equal to X is an odd integer larger than 1. A union B is equal to 2, 3, 4, 5, 6, and so on. In the illustration, it shows the intersection event. The intersection event A intersect B is the event that happened when both A and B occur. It takes only the elements that are in both sets. Intersection contains the elements that the two sets have in common. The intersection is where the two sets overlap. Example, let A is equal to ABCD and B is equal to BDE. Then the intersection between A and B is equal to BD. As we can see on the illustration, the elements B and D are the only elements that are in both sets A and B. In the illustration, it shows the complement event. The complement event of A is the event that happened when a doesn't occur. So complement of an event is all other outcome, not the ones we want, and together the event. And its complement makes all possible. An event is a subset of outcome in a sample space that are not in the event. Let's say we are rolling a standard 6-sided die and our event A is rolls as 5 or 6. Our complement A would then be roll A 1, 2, 3, or 4. We can illustrate this as follows. The event rolling A 5 or 6 and its complement rolling 1, 2, 3, or 4. The events are mutually exclusive and exhaustive. Let's take the probability of event A and the probability of complement event A. Event A is 5 or 6. Its numbers of ways it can happen as 2. The total number of outcome is 6. The probability of event is equal to 2 over 6 or 1 over 3. The complement A is 1, 2, 3, 4. The number of ways it can happen as 4, and the total outcome is 6. So the probability of complement event A is equal to 4 over 6 or 2 over 3. Probability of events plus the probability of complement event is equal to 1. Event A plus all outcome that are not event, A make up all possible outcome.
A birthday paradox or a birthday problem. In probability theory, the birthday problem or the birthday paradox concern the probability that in a set of n randomly people, some pair of them will have the same birthday. When we say birthday paradox, is a problem where you find the probability of two people having the same birthday in a certain number of people. How many people do you think it will be take to survey, on average, to find two people who share the same birthday? Due to probability, sometimes an event is more likely to occur than we believe it to. In this case, if you survey a random group of 23 people, there's actually about a 50-50 chance or 50% chance that two of them will have the same birthday. This is known as probability paradox. To able to find the probability of having a same birthday, let's make it simple. No twins, no leap year, no pattern by suggested parents. In a group of 23 people, the probability of having a shared same birthday is 50%. Then a group of 50 people has 97%. While a group of 75 people has 99.97% and a group of 100 people has almost 100% chance of a same birthday. How it's possible that few people have a chance of sharing a same birthday? In order to find the probability of having a same birthday, first, we're going to find the probability of not having a same birthday. For example, let's try to find a chance of having a same birthday in 23 babies. This table shows the probability of not having a same birthday. To simplify this calculation, we can write it 364 factorial. So, We start in 364 because 365 over 365 is just a 1 over 342 factorial. 342 because 365 minus 23 babies is equal to 342 times 365 days raised to 22, which is 23 minus 1 is equal to 22. To formally understand, let me show to you the formula. This will be the formula how to find the probability of not having a same birthday. With the help of this formula, we are able to find the probability of having a same birthday between 23 babies. Let's disregard 365 over 365 because it is equivalent to 1. So, it will be 364 factorial. To able to find the 342, you're going to solve 365 minus the number of babies, which is 23 babies, times 365 days raised to 22. To able to find 22, we will subtract 23 minus 1, which is equal to 22. 364 factorial over 342 factorial times 365 raised to 22, and we solve the whole equation as 0.492703, which is 49.3%. And remember, that's the probability of not having a same birthday. To able to find the probability of having a same birthday, so we will subtract 0.492703 to 1, which is equal to 0.507297 or 50.7%.